Hello, my name is Bahit Nurashevna Alipova. I'm Associate Professor of International Information Technology University, Department of Mathematical and Computer Modeling, and today's lesson in framework of course Methods of Nonlinear Programming, and today's topic is Constraint Optimization, Lagrange Multipliers. I made this lesson according to slides of Professor Dmitry Bertsekas of MIT. So, enjoy today's lesson. Today we will consider equality of constraint optimization problems, and we will set the stage for discussing Lagrange multiplier theory using two different proof techniques. First of all, we will consider equality constraint optimization problems, and we will consider function assumptions for such kind of problems, and topics which will be covered in this lecture. This is basic Lagrange multipliers theorem, this first order optimality condition, a necessary condition for optimality under equality constraints, introducing Lagrange multipliers lambda I. And we will consider the first proof elimination approach, which reduces the problem dimension by eliminating constraints using the implicit function theorem or coordinate transformation. And the second proof, a penalty approach, which introduces a penalty term. For example, squared norm of the constraint violations to convert the constraint problem into an unconstrained one. Let's go to consider this in details. This slide elaborates on the Lagrange multiplier theorem for equality constraints and provides second-order necessary conditions and illustrates the concept with graphical and numerical examples. So the first one, the first order of necessary condition Lagrange multiplier theorem. So let x star be a local minimizer of the problem of minimization and subject to hix is equal 0. Assume that x star is a regular point, meaning the gradients of the constraints are linearly independent. Then nabla f of x star are linearly independent. Then there exist unique scalars lambda 1 and so on lambda m stars, the Lagrange multipliers, such that the nabla and of this function plus this sum multiplying with nabla hi is equal 0. And this is called the first order Karush-Kuhn-Tucker KKT condition for equality constraints. Second order necessary condition, if a, f and h are twice continuously differentiable, then we also requires all this inequality, and we can tell about expression inside the parentheses is the Hessian of the Lagrangians, and these Lagrangians, the condition says that the second derivative of the Lagrangian is positive semi-definite on the subspace tangent to the constraints. Let's consider two graphical examples. For example, here, minimizing x1 plus x2 subject to x1 squared plus x2 squared is equal to So then objective contours are straight lines x1 plus x2 is equal constant. Constraint is a circle of radius squared 2. At the optimal point, x star I'm sorry, just a moment. So, at the optimal point, x star is equal minus 1, 1, as the gradients are nabla f of x is equal 1, 1, and nabla h of x is equal 2x1 to x2. And then it's equal minus 2, 2. So, from this diagram, we can see the gradients are parallel but not opposite, confirming stationarity. And Lagrange multipliers is equal lambda is equal 1 over 2. For second graphical example, the right one, I can tell that a similar visuals is shown for minimum x1 plus x2 subject to h1 of x is equal x1 minus 1 squared plus x2 squared minus 1 is equal 0, and h2 of x is equal x1 minus 2 squared plus x2 squared minus 4 is equal 0. There are two circles centered at the 1, 0 and 2, 0 with radii 1 and 2 respectively. At x star is equal 1, 1, the constraints are satisfied. Gradients of h1 and h2 are linearly independent at x star. Optimality conditions apply. So summary for this slide: first order condition ensures stationarity via a linear combination of gradients. Second order condition ensures that the candidate point is at least a local minimum. Examples visualize how these gradients and constraint boundaries interact at optimal points. In geometric intuition, at the optimum, the gradient of objective is perpendicular to the constrained surface. Now we can consider some example of Lagrange multiplier methods, in which you can see here that we need to minimize the function x1 plus x2 subject to x1 squared plus x2 squared is equal to. So at first define the Lagrangian, and here we have our function plus lambda multiplying by our constraint. So we have constructed the Lagrangian. Take the gradient and set equal to 0. We will take partial derivatives in different directions, in directions of x1, x2 and lambda of our constructed Lagrangians, and equalizing each of them to 0. Then solving this system of free equation. The first one solving the first and second equation and receiving such kind of correlation for x1 and lambda and x2 of lambda. And here we have this correlation between x1 and x2. Now substituting what we have received to the third equation and multiplying them, equalizing them, and receiving as a result x1 is equal plus minus 1. So we have actually two candidate points. The first one, x1 and x2 is equal 1, so the point would be 1, 1. And here we have a Lagrangian multiplier minus 1 over 2. We have here such kind of correlations. And the second point, x1 is equal x2 is equal minus 1, so the point is minus 1 minus 1, and a Lagrangian multiplier is equal 1 over 2. Now we need to choose a minimizer from both these two candidate points. So we want to minimize our function x1 plus x2, and we can compute this in each our candidate points at 1, 1, at minus 1, minus 1. And now we have received 2 and minus 2. For sure we will choose the minimum from these 2 points. So the minimum occurs at point x star is equal minus 1 minus 1 with a Lagrange multiplier equal 1 over 2. So we have solved our problem minimizing the function x1 plus x2 on this constraint set. Let's explain how to handle equality constraint optimization problems where the constraints are linear equations ax is equal b. It uses an elimination method to convert the constraint problem into an unconstrained problem and then derives the Lagrange optimality condition. So let's consider the original problem with linear constraint. We need to minimize the function f of x, and to subject to ax is b is equal b, and where A is m by n matrix with linearly independent rows, and B from the set Rm is a given vector. And here Rm is continuously differentiable, and rank matrix A is m, and B is a constant vector. Now we are making partitioning the variables. We split the variables and the matrix A to two parts B and R, where B is m by m invertible and x is equal transpose vector xb xr. And now the constraint becomes ax is equal bxb plus rxr, so is equal b. Then we can receive xb is equal b invertible multiplying by b minus rxr xr, subject to some new constraint area xr from the set Rn minus 1. We would like to eliminate the constraints, and now we will have a new substitute xb into f, and we will receive such kind of, as I told, some new constraint set. And now we have received unconstrained optimization problem. First order optimality condition for unconstrained minimization, in which nabla f of xr star is equal 0, and we are applying the chain rule here, and then we will receive such kind of equation like 1, and define Lagrange multiplier as follows. Lambda star is equal minus b dash invertible multiplying by gradient on b function of f x star. And from 1 we can get such kind of correlation in which a nabla of this function, gradient of this function plus b transpose lambda star is equal 0, and then we can rewrite the equation 1 in following form, where the gradient on r function of x in the point x star plus transpose a matrix R multiplying by Lagrange multiplier lambda star is equal 0. So combining this, we'll receive such kind of correlation, like gradient of function f in the point x star plus transpose A matrix multiplying by Lagrange multiplier is equal 0. And this is exactly the Lagrange multiplier optimality condition for minimizing of function f of x subject to ax is equal b. So, telling about summary of the method elimination approach. So the first one, we are using the constraint ax is equal b to eliminate some variables. Solve for xb. Then we reduce the constraint problem to unconstrained one in terms of xr. Then we apply unconstrained optimization techniques and recover the Lagrange multipliers explicitly from the chain rule as follows. Continuing this elimination approach, we can tell that we are continuing this discussion of second order conditions in equality constraint optimization with linear constraints and use the elimination approach. It carefully derives the form of the second derivative of the reduced function and connects it back to the full second order Lagrange condition. So still we are solving this problem. We are minimizing the function f of x subject to ax is equal b, and which using the elimination approach will becomes minimizing of function xr is equal fb inverse matrix of b multiplying by b minus rxr on xr. So for a local minimum at xr star, yes, the second order necessary condition is following. I mean the equation number 2. And now we are calculating the Hessian nabla squared function f r star, and this step applies the chain rule for second derivatives to the reduced function f r star as follows, and where xb is equal b multiplying by transpose b inverse matrix multiplying by b minus rxr. After calculation, the resulting expression is equal such kind of correlation. Second partial derivatives of this function, Hessian. So this is a reduction of the full Hessian of function f into a form acting only on xr using chain rule and implicit differentiation. Now we need to link to the full space second order condition. We know that constraints are linear, so the second derivatives vanish, and you can see this here. And from the equation 2, from this equation, the reduced Hessian will be becomes like that. I mean such kind of correlation. because of the second derivatives of h I x as 0. Yes, h I x is 0. The Lagrange form remains valid. Then we need to construct y from D. We define y as follows. This is transpose vector column like yb, yr, and it would be looked like first element is minus inverse brd and d, and this vector satisfies such kind of correlation. So y lies in the null space of Jacobian of the constraint, meaning it's a feasible direction tangent to the constraint surface. So final result, this is actually a second order Karush-Kuhn-Tucker condition for equality constraints. Summarize. The function is reduced using the elimination of linearly constrained variables. The second derivative of the reduced function is computed explicitly. It's shown to match the second order Karush-Kuhn-Tucker condition in full space using a constructed direction y in the null space of A. And this validates that the elimination method respects both first and second order optimality. Here we present a penalty method proof of the Lagrange multiplier theorem for equality constraint problems. It constructs a family of unconstrained cost functions that incorporate a quadratic penalty on constraint violation and regularization term to prove that minimizers converge to the solution of the constraint problem. So, from the beginning, we will consider penalty function definition. Define the penalized objective function as follows. So f(k) of x is equal such kind of correlation, where f of x is the original objective function, h of x is a constraint. For example, we want h of x is equal 0. K from n increases the to penalize infeasibility more strongly. Alpha positive is a fixed regularization weight. X star is a known local minimum of the constraint problem. This penalty function encourages both at constraint satisfaction h of x is equal, tends to 0 and proximity to x star via the regularization term. So let epsilon more than 0 and we will consider feasible set and minimizer of penalized problem. Define a closed sphere around x star, and we will consider here S as follows, in which x from such kind of area which is less or equal very small epsilon. And we assume that the function f of x star is less or equal function f of x for all feasible x from S such that h of x is equal 0. So let's consider like k is equal argument of minimum of fkx on the x from S. And now xk is a minimizer of the penalized problem within the ball S. Key inequality and behavior as k tends to infinity. At the minimizer xk, we have such kind of correlation. This holds because xk from the set S, x star from S is feasible, so we can tell that fk of x star is equal fx star plus 0 plus 0. So we actually making this stuff equal to 0, hence fk of xk is less or equal fk of x star. And from this we can make the step first, in which we can consider that k over 2 such kind of term is less than f x star minus f xk minus alpha over 2 the squared norm of this distance, as k tends to infinity for the left hand side not to diverge, so we must have this limit. It would be equal to 0 for any limit point x dash of xk. Furthermore, from the equality f xk plus such kind of multiplication and less or equal f x star, but since x dash from set S and h x dash is equal 0, we know that function fx star less or equal function of x bar by assumption of optimality of x star. So combining both of x, we will receive that x bar is equal x star. So we can tell that such kind of sequence xk tends to x star. So we are receiving actually convergence process here. So minimizing the penalized function fxk of x in a neighborhood of a local minimum yields points that satisfy that h of xk tends to 0 and approach x star demonstrate that x star satisfies unnecessary optimality conditions for the equality constraint problems. This is a proof of Lagrange conditions via penalty approach, and it used a penalty term to softly enforce the constraint h of x is 0, a regularization term to keep iterates near x star, a limit process to derive properties of x star. Here we conclude the penalty approach proof for deriving the first order Lagrange multiplier condition and mention the pathway to the second order condition. So context recap, we are minimizing a penalized function And previously we showed that xk implies to x star, h from xk implies to 0, and xk eventually becomes an interior local minimum of fk in a small ball around x star. So, first order necessary condition for unconstrained minimizer. At an interior local minimizer xk of fk, the gradient vanishes. So it means that the gradient of such kind of function is equal 0. And we can demonstrate all this stuff which we have considered on the previous slide. Now assume for the large k nabla h of x star from the set R with n by m dimension has full column rank m, which is thus near x star, since such kind of gradient is full rank. Then this matrix multiplying this transpose gradient of h and in xk multiplying by gradient of h of xk is invertible, so we can left multiply equation 3 by such kind of transpose gradient to isolate the multiplier k, h, and of xk. And now these expressions define an approximate Lagrange multiplier in form 4. Taking limits sk to infinity and xk to x star, we can receive all this explanation that h xk tends to 0, nabla f of xk tends to nabla f x star, nabla h xk tends to nabla h x star, and then from the equation 4 we obtain the limit such kind in the end of that we are taking this absolutely equal to lambda star, and this defines the Lagrange multiplier vector lambda star. So substitute in the first order equation. From the equation 3 we received this sum will be equal to 0, and take the limits as k tends to infinity, and noting that alpha multiplied by xk minus k star x star tends to 0, and kh of xk tends to lambda star, so we get such kind of correlation. And this is the first order Lagrange multiplier conditions. Final notes and about the second order condition, we note that derivative second order of Lagrange condition use the second order this necessary condition for unconstrained minimization of fk, and let k tends to infinity and apply algebra as previously done in earlier slides. We can summarize that minimizing a penalized function fk yields iterates xk to x star. Using the unconstrained first order optimality condition, we can derive this condition, and penalty method. Those prove the existence of Lagrange multiplier lambda star, satisfying the Karush-Kuhn-Tucker condition. Let's consider here some idea of penalization. This explanation for my students. This is a penalized function or penalty function is a way to solve a constraint optimization problem by transforming it into an unconstrained problem. So the main idea of penalization, instead of constraint optimization problem, we solve an easier problem by introducing a penalty term for violating the constraint. So here we have our original objective function f of x, and the second term is like penalization term. H of x is a constraint function, and k positive is a penalty parameter, usually increasing over time. So if x satisfies the constraint, then h of x is equal 0. So we have not having such kind of term. And then our penalization function is equal our original objective function. If x violates the constraint, then this norm, squared norm of h of x, is positive, and we can add our penalty to function f of x. As k tends to infinity, any violation gets more costly, and the solution is pushed toward feasibility. So this is the main idea of penalization. A little bit more extended idea of penalized function with regularization. So we consider a penalized function as follows. So we have considered our objective function initial and then a penalization term, but here we have added regularization term, alpha over 2 multiplying by norm, squared norm, distance between x and x star. It keeps the iterates close to a known solution x star to localize the minimization. So the main idea again of regularization. It turns a constrained problem into unconstrained one. We can use standard optimization techniques, for example, gradient descent, Newton's method, and so on. It helps prove theoretical results like the Lagrange multiplier theorem. Now we consider a textbook illustration of the Lagrange multiplier method for equality constraint optimization and include a simple quadratic minimization example. Actually, we have considered already how to find Lagrangian multiplier before in some example, but I would like to repeat here. So, we define the Lagrangian function as follows for optimization problems of the form of minimizing the function of x subject to hi of x is equal 0. And we define the Lagrangian as follows. In here, x from Rn, this is decision variables, and lambda I, this is Lagrange multipliers, one per constraint, and hi of x, this is equality constraint function. Then Lagrange multiplier condition, like Karush-Kuhn-Tucker for equality constraint. So if x star is a regular local minimum meaning the constraint gradients are linearly independent, then the necessary conditions is as follows. This is for stationarity and this one for feasibility, in which 1 over x gradient and the second over with respect to lambda, and this is for h of x star is equal 0. And we are receiving the system of n plus m equations in n plus m unknowns, the components of x star and lambda star. And a second order condition for minimum we can represent as follows. So transpose vector y multiplying by Hessian, and this Hessian of Lagrangian with respect to x, and y is direction tangent to the constrained surface at x star. Again, I would like to show some example, and this visualization captures the core idea of the Lagrange multiplier method. The gradient of the objective is normal to the constrained surface at the solution. And here we can consider the constraint geometric optimization interpretation of our problem. So we consider we need to minimize the function 1 over 2 x1 squared plus x2 squared plus x3 squared. And here this gray spheres represent level set of the objective, this function, growing outward from the origin. And subject to minimize on this set, on this constraint, x1 plus x2 plus x3 is equal 3, and this is a colored surface. This constraint, I can name this like constraint plane. And the red dot here marks the optimal point x star with coordinates 1, 1, 1, where the sphere first touches the plane, minimizing distance to the origin while satisfying the constraint. So we have objective function, we have constraint. And the objective function, this is actually this half the square of the Euclidean norm, like 1 over 2 norm of x squared. So the level sets of fx are spheres centered at the origin. And a constraint set defines a plane in 3D case. So the feasible region is the intersection of this plane with 3D sphere somewhere. And what's happening geometrically? We are looking for the point on the plane, the constraint plane that is closest to origin, because of minimizing of this half squared norm is the same as finding the closest point to the origin. And so now we are constructing Lagrangian in this form, in which the first term, that's actually the function itself, and the second, this lambda multiplying by constraint. And then we are finding the partial derivatives in each direction, and including direction with respect to lambda, and finding the solution of all these 4 equations. And now we are substitute each equation to find the set of function, the set of points, sorry, and then the function is minimized when the variables are as equal as possible, subject to their sum being free. and the result xi star is 1 for all I confirms the balance. So optimal value of function f of x star is equal 1 over 2 plus all these ones, so that's equal 3 over 2. So we have found the coordinates of the point. This is 1, 1, 1, and a value of the function by 1, 1, 1 here. This is 3 over 2. So we have minimized its function, finding the Lagrangian function. Let's consider another mean variance portfolio optimization problem as example, a foundational model in modern finance introduced by Harry Markovich. So, we have 1 unit of wealth amount to invest across n different assets. Each asset I has a random return AI with mean AI bar and expected return and covariance matrix in this form, which measures the joint variability of returns. So let xi be the fraction of wealth invested in asset I. Define x is x1, x2, and so on, xn transpose. Then we need to minimize the variance of the portfolio return, a measure of risk. And here the sum of xi is equal 1. So we ensure that all money is invested. And this multiplication, sum of multiplication of AI bar and xi is equal m, sets the target expected return. So optimization problem, we want to minimize risk, variance of return, while satisfying constraint here that we need to minimize xt multiplying by q and x subject to sum of xi is equals 1. This is budget constraint. And the second constraint, this is target expected return, should be fixed. And this is quadratic program with 2 linear equality constraints. So let's consider this in form of Lagrangian formulation. Define Lagrangian function with 2 lambda 1 and lambda 2 Lagrangian multipliers. And here then we will consider this in form of such kind of form in which u is equal 1, 1, 1, and so on transpose, and e bar equal 1, e1 bar, and so on, en bar transpose as following, I mean such kind of assets. And then the first order optimality conditions we can consider if we have the gradient of the Lagrangian equalizing to 0, then this one, 2q x star plus lambda 1 u plus lambda 2 e bar is equal to 0, then this is a linear system, an x star, involving the matrix q and vector u and e bar. In this solution, in this case, we can receive the general solution form x star is equal mv plus double v. And here v and double v are vectors that depends only on q and e bar. And m, this is the desired expected return level, if you remember our constraint. And it gives a parametric family of optimal portfolios, one for each m. Then the resulting risk, the variance of return, the resulting variance is equal sigma squared is equal alpha m plus beta squared plus gamma. And here alpha, beta and gamma are scalars that also depend on q and e bar. And this is a parametric equation of the efficient frontier, a parabola in the risk-return space. It describes how much risk you must take to achieve a given return m. So this is actually, we can represent this in geometrical form like that. And here this line for given m, the optimal sigma lies on the line called efficient frontier. And this is a classical convex quadratic optimization with a closed form solution. And the solution balances maximizing return and minimizing variance. The efficient frontier result from varying m and plotting sigma squared versus m. So actually here we have considered some real problem from finance, so it could be helpful for future. Finalizing this last lesson in framework of this course, Methods of Nonlinear Programming, I would like to repeat again that I have used the slides of Professor Dimitri Bertsekas for nonlinear programming of MIT. And if you will have some question, just revert to me. Thank you for attention. My name is Bahit Nurashevna Lipova, and it was a course in framework of methods of nonlinear programming, and it was course of Lagrangian multipliers. If you will have some question, don't hesitate to contact me and follow an email. Thank you. Bye.